What's up everybody, I am back with another video for MDA 1. And the reason I'm making this video is because I must admit I have caught myself out forgetting some of the basics. And what I'm really speaking to here is just to put everything back in context of what we learned at the beginning. And if we're speaking about roofing, I want to go back and say, well, what are these foundations that we learned last month or 2 months ago, and why have we built on that and sort of forgotten the foundations? Because these foundations often come up in assessments. So I want to go back, take a look at some of these basics, and hopefully reveal some sort of insights that you have forgotten. So I've got a page in front of me, back to the basics. There's 9 points here. I just want to go through each of them quickly and then we'll move on to the drawings. So understanding layers in beam roof construction. This is something I must admit I forgot. And when I opened up this drawing, I think it was Carport 03, this drawing, it made me think. And even though I remember the work, I found myself, being thrown off a bit, because there's room here for a question that could throw a lot of us off. So number 2, monopitch and double pitch. What I've noticed here is that there are sort of there are different rules that apply to the two. Obviously, we'll go through them, and I also want to go over the calculation and why it is different for your exposed ends at your eaves versus your exposed ends at your verges. So that is an interesting one. We'll cover that. Structural versus non-structural items, point 3. I wouldn't say that's too interesting, but I threw it in there because sometimes you may wonder, well, I'm doing gang boarding. How come I don't put greater than 2.4 meters but not exceeding 3.9? And the reason is that it's not in the standard system. Anyway, we will get to that. Connections in trusses. This one is interesting just because you have to play around with the visualization of your timber in planes. So you've got to visualize, okay, these two timbers, they might be meeting on the same plane, and that would mean it needs a nail plate. If they overlap, then it's going to have a bolt. So we're going to take a look at that and scenarios where maybe you have both a nail plate and a bolt. Interesting. We're going to have a situation where you need to add a king post. Point number 5, that is where you're not given a half truss. Maybe you need to figure something out about how to support the center of your half truss when it's not given as a section, and you're going to have to add a king post. Point number 6 is an interesting one. I enjoy this because this is sort of the mathematical side of problem solving on plan, and just to sort of go deeper into the theory of how and why we can do the interesting things we do with jack rafters. And what I mean by that is taking fractions of a full rafter and then dividing that up and multiplying it to get a length for a jack rafter. That to me is pretty interesting. So we're going to cover that. Point number 7 is another interesting one. We're going to apply trigonometry to go forwards and backwards. So we're going to take on flat to on slope, and then you're going to go backwards for on slope to flat. And I'll cover examples where that is done. I'm sure you already know about those examples, but let's just go over it for the sake of revision. Point number 8. Purpose-made tiles is an interesting one. I'll just go over, the theory of why we need a purpose-made tile and instances where they go. It's not always straightforward because on plan, it's difficult to visualize valley versus sort of hip ridges. And it's easy to slip up and put purpose-made tiles where they should not be. So we'll go through that. And finally, point number 9, parapet walls, flashings, and a double flashing scenario. This is something I picked up yesterday and I thought I would share it. Okay, so let's head over to point number 1, basic layers in beam roof construction. So this is Carport 03. What I want to point out here, guys, is that we've been very busy with trusses and sort of advanced roof systems, and we've forgotten how a beam roof structure works, or at least I have. So when I looked at this, I was a bit surprised. So a couple of rules to take note of. Here is a primary beam. And what this means, and here's our nice cross-section of a primary beam, the one end is actually bearing on the column, so there's no connector for that main beam. And the other end over here is going to be fixed into a wall. And what do we put there? I'll get to that just now. So that's layer one, guys. At the bottom, we're going to have a main beam. After that, we're going to have a secondary beam. It's going to rest on top of our main beam. So all of these, 1, 2, 3, 4, these are secondary beams bearing down. Let's use a different color. Let's go for red. They're bearing down on this main beam. And there are 4 secondary beams, right? That's what's interesting here is that the secondary beams, they're also going to be fixed to the main beam and then fixed to the wall. And how is it fixed to the wall? And how is it fixed to the main beam? And then finally, on top of that secondary beam, we're going to have purlins, which run the same direction as our main beam. Let me not use yellow. Let's go for purple. No? Fine. Okay, those are purlins. That's your third layer, your top layer. Okay. Now, your purlins are fixed to your secondary beams. And how are they fixed to your secondary beams? We're going to take a look. Let's use that one as an example. So, for our first question mark, main beam to brickwork. Okay, that is an Eco 38L. It's actually a truss hanger, right? Okay, on that side. And it comes with 4 M12 expansion bolts. And expansion bolts are pretty awesome, I'll be honest. I absolutely love them. Once you've drilled your hole into the cavity, or into the brickwork, sorry, you actually put your bolt in, and as you tighten that bolt, it's going to start applying pressure outwards. And what usually happens is you have maybe some sort of threaded item here. It's going to, as you twist this threaded item, you're going to twist the head. The threaded item is going to start expanding the sort of sleeve that it's in and apply a outward force onto the brickwork. And you keep tightening, and it keeps forcing and expanding. And this, well, okay. This expansion bolt is trying to push outwards and the brickwork is resisting it. And then you have quite a strong bond, quite a strong sort of anchor. And a lot of these wall anchors work like this. Yeah, there's a huge variety and they all employ a similar idea where you're expanding something and forcing outwards against brickwork. So that is the story with our main beam to brickwork. Here, we have a main beam simply resting on a column. And what do you do here? Well, the answer is absolutely nothing. It's just resting there. They're going to actually they might bed the timber in brickwork, which is what looks like is what's happening here. It is bedded in the brickwork. You would have one course on that side, or one skin on either side, and probably mortar around it, just to hold it in place. That is the main beam. The secondary beams is another story. The secondary beams which bear on the main beam, they come across here to brickwork. And let's just take a look at what our dimensions for secondary beam is. 38 by 228 is our main beam, and 38 by 114 is the secondary beam coming up to here. And I am tempted to say you could use a truss hanger there. But I do know of instances where there's angles, and to be honest, I can't elaborate further on that. You need to investigate what goes there between a secondary beam and brickwork. I won't say any more on that because I personally do not know. But where secondary beam meets the main beam, we're going to have what's called a eco hurricane clip. Okay. And after that, we're just left with the purlins. And we don't specify how the purlins are fixed, but I would suggest it is probably the serrated roofing nails. If you want to research that yourself, you can. They're just nails that have sort of a texture along the pointed end, you know, that penetrates the wood. And this texture sort of adds to the friction, the frictional force between the timbers. It's holding together. So it's sort of like this, and then it's sort of ridged. That's what a serrated nail looks like. You check it out. It's pretty interesting. At least I think so. So that is the story with a beam roof construction. Is you've got these layers on top of each other. Just understand what's bonding to what, and apply your connectors, and you will be good to go. Point number 2: monopitch versus monopitch versus double. Let's just take a look. It's drawing 2 and 4. All right. So here we have an example of both. We have a double pitch and a mono pitch. And what I actually really want to point out is we have one side of 4 purlins. Okay. And when you're describing your double pitch, what you're going to do is you're going to say 4, and there's 2 sides to it. So you're going to do your description, but you're going to say there's 4 items one side times 2 to get both sides. Okay. And that'll be it. When you do your mono pitch, you only going to have your 4. You don't times it by 2. This applies to basically everything. It'll include if you have exposed ends on your eaves and verges. And I just want to expose timbers and fascia boards. So what this means, the implications of that, on this side you have 1. If you were to have a barge board, you'd have 1 and it'd be running along that slope. On this side you'd have 2, so you apply it twice. Okay, 2 barge boards on that gable end if you had barge boards there. And the same is true for your fascia boards. Let's find a plan view. We'll take this one. So your fascia boards for a double pitch run like this. And actually, I have to correct myself. The mono pitch also has fascia boards on both sides. It's just that this example, the mono pitch is connected, so you don't put your fascia board there because you can't. But a standard standalone mono pitch will actually have a fascia board on both verges, right? Sorry, both eaves. The one eave is just higher up, the other eave is lower. And then your mono pitch verge will also have your barge boards. So those will be the same, but what's interesting is the difference in calculation for your fascia boards and your barge boards. So fascia boards are running with your building. So let's just make a nice little drawing here. And since fascia boards are running with your building, they don't get a factor. You don't multiply it with a factor, right? Here's your fascia board in red. Since it's running with the building, no factor. If you are doing a barge board, it runs up the slope. You need to apply a factor. If you do not apply a factor, you are basically measuring what's down here, and that is not where it goes in real life. So that is an interesting sort of difference between the two, and this difference carries through to other things. So the same is true for when you come to exposed ends for your purlins. So here's a good example. Let's zoom in on this. Here we have 150 overhang, and it's a mono pitch. Now I'm just going to find so I can show you what it looks like. Here's what it looks like, mono pitch up to a parapet wall. What you're going to have is purlins running along the top. Or in this case, because it's tiled, it's going to be battens, right? But either way, I'm trying to explain something interesting. And what's interesting is that these purlins actually have exposed ends. That's right. If there is a little bit of overhang, these purlins actually come across. Sorry, I'm just drawing a little piece, but they actually run like that. So they run across and they will be exposed. That means you need to account for them under eaves and verges. And that little 150 overhang, you're going to apply your, well, actually not going to apply anything. I need to correct myself. It is taken as 150 straight. So these purlins are 150 over, and you're just going to have to multiply by the purlin perimeter. So let's say it's 2 times 38 and 2 by 50. And you're going to say, well, Anthony, that's a bit weird because I haven't been doing that. Well, we have been doing rafter ends on slope have a factor involved. Now, I don't think there's any scenario where you, yeah, I guess there could be a scenario where your purlins are on slope, but in your rafter ends on this side, this case, it needs a factor. So even though its overhang is 400, it's given, this 400 here, you're going to have to convert to an on-slope dimension to get what this actual exposed piece of timber is. So when timber is running up the slope, you're going to need a factor. When it's running sort of along the slope, there's no factor involved. And very rarely, as I've seen, do we get a chance to practice this phenomenon here, where there actually is some exposed ends that aren't with slope. They aren't being applied. So just watch out for that. That does happen. You will be asked to measure it occasionally, and it will throw you off. You've got to understand the running with the slope versus running along the slope. And if you get that right, I don't think you'll be caught out. Let's go back to the basics here. So I've explained the barge board and fascia boards. The one runs with the slope, the other one along the slope, and it's the same with the timbers on eaves and verges. Your structural and non-structural items, every now and then I just catch myself sort of wondering, like, okay, is this item less than 2.4, or do I just say it is as the description is and not include this? So basically you just need to know it's wall plate, battens, purlins, tilting fillets, and your gangboarding I've added, because gangboarding in all of our memos we did not include it into those categories of timber lengths in the standard system. So that is pretty straightforward. Connections is an interesting one. I'm going to go over to drawing 3. Let's see what I got here. So this is interesting because I thought, well, here's a scenario that I don't think we've encountered. We have a situation where these two pieces and those two pieces happen to be overlapping, so that's fine. You're going to need a bolt through that. So there's an M10 and an M10 on either side. But once they come together, they're actually meeting flush. So now you need a nail plate. It's a 100 by 150 by 1.2 nail plate. I thought that's interesting. You've kind of taken two components, you've bolted them, and now you've brought those bolted pieces together. And now how would you fix this? you're going to have to nail plate it. And that was a scenario I don't think I've seen before. So I thought I better share this. You're going to put a nail plate across there, and you're going to have your bolts 1, 2. All right, that should make sense to you, because now you got, as a top view, you got timber, another piece of timber. Okay, and since it's sloped, you don't really see as much of it. Let's just draw that like that. Okay, this one's a rafter. This one's your, let's call it a strut. You're going to have your bolt running through. That's your head of the bolt. Oh, let's go all the way through. Okay. Bolt. And then basically you've done the same thing on the other side. And then you're going to have to connect these two. And since there's no overlap, you're going to have to use a nail plate. Okay. If there was an overlap, you would have a very tricky time calculating how long this bolt needs to be. It would be really long. But in this scenario, it's actually 2 bolts and a nail plate. Right? Nail plate on that side. And that is that. Probably put a nail plate on both sides, but anyway. Now the reason we do that is there's a whole story of dotted lines versus not dotted lines, where they meet flush versus sort of follow through. In this case, they follow straight through. You can see that this timber behind it has a dotted line. It indicates that it's going to the same endpoint, and you're going to need a bolt. The same is true here. That is a bolted connection. Here is a situation where there's 1, 2, and 3 pieces of timber. And this is interesting because what you'd have to do is break it down into 3 times. Let's say we need to take a look at what these thicknesses are. Let's say they're all 38, okay? And from there, you're going to have to add your 2 times 16 because it's already in the 16 mil category. This was 114, and this was 32. So what you get is 146. You round up to 150. So over here is a 150 mil bolt, guaranteed, because all 3 pieces go through that point. And that is about it for this scenario. But I thought, you know, this situation here is interesting. It is pretty interesting because you usually nail plate one component that meets one component, right? That's what we've seen typically is this piece, if it ends short, you're going to nail plate it across. You can agree with that, but it's very interesting to see now that we have 2 pieces bolted and they meet flush. You're going to have to nail plate it somehow. So that is my commentary on that. Let's just take a look at what else I've got here. Just page 3 and 4. Let's see what 4 has for us here in this regard. So here's a scenario where we have bolts and nail plates side by side. It's not particularly revealing like the other one. The other one had, you know, quite an interesting sort of setup. Here we have, okay, that's a typical nail plate scenario. So 2 pieces of timber coming up to each other, they don't follow through like here, and that means they get a nail plate. 1, 2, 3. Okay. Here you're going to need 1 nail plate across here and another one to come down and attach to your king post. So these are the typical scenarios that you would see. The other one was, you know, a bit odd to take note of, but I thought I'd share it. So number 5, let's take a look at king posts. Oh, that's interesting. Okay, hold on. Let me back it up to number 4. So what I said here for number 4 is deciding on how many split ring timber connectors. This I've picked up as something I've overlooked. I'll be honest, I've overlooked it for a while and sort of just assumed that there's a certain number for M10 and a certain number for M16, right? But there's a reason. So a split ring timber connector is something that goes around the bolt and between the other piece of timber. This doesn't really make too much sense structurally, but for the sake of example, your bolt running through your timber, through your split ring, and through the other side. You need one split ring timber connector per timber to timber interface. So there's one piece of timber, there's two pieces of timber. That means you need one. Okay. If you had a third piece of timber here, you'd need another. Sorry, I need more space to add my timber connector. You'd need another one if you wanted to add another piece of timber on this side. So for every timber to timber interface, you need a split ring connector. And the reason is these timber connectors have teeth. And the teeth bite into the wood on each side and sort of add to the bonding and structural integrity of that joint. So when we say that an M10 automatically gets 1 and an M16 automatically gets 2, what we are referring to, and I'm sure you've picked this up already, is that if 1 means that there's only one interface between a 38 and a 38. And because there's one interface, you need one timber split ring going to go over there. Okay. Now for M16, if you're saying this to, you are going to put it okay, almost there. We are going to put it 1, 2. So that is the reasoning behind it. And, I must admit, I usually just do it automatically. I don't even think twice about it. But it's important to actually start thinking about this stuff, because as soon as you start doing things automatically, that's when you get caught out. So take note of that. There is reasoning behind it. You need to visualize how many pieces of timber you're going through, how many split ring connectors there are, and your bolt length. Let's move over to point number 6. Adding a king post. So for this one, take a look. I wanted to take this as an example. We've been given a full truss, but what I want to really just think about is a scenario where you don't have a section for a half truss. And what I've seen in the past is that the sort of measurer, the quantity surveyors, is required to cut it in half and add a king post themselves. And when you add your king post, you need to be very careful about how you do it. And I guess you can decide what happens at this connection. You could follow through, in which case you would need a bolt, or you could stop it short and use a nail plate. But there are scenarios where this could come up and they will ask you, and you're going to have to use your own brain to figure out and design a king post and a half truss. And at this top section, because you got 1, 2, 3 coming through, you might have an M16 there. Maybe you want your king posts. I don't think they stop short. I think they typically go through. So you would use a bolt. That is the story with the king posts. Point number 6 is quite interesting. I really enjoy this theory. So let's just take a look. Drawing number 4. So what I'm saying about the rise over run theory is that it's really basic mathematics when you look at a graph and it's on a 45-degree slope. Okay? And all that is saying is that for 1 unit of x to the right, our rise is also 1 unit y. So rise equals run. That's all we're saying. So That's for a perfect 45 degree. And often we are applying this rule where for every 1 unit this way, we're moving 1 unit that way. And then if this is 2 units this way, this is 2 units up. So all you have to do is visualize that this is our 45 degree graph. And it'll all start making sense. And suddenly your eyes will light up and you'll say, this is amazing, because it is. That is a 45. Okay? And then you could say 1 unit to the right is the same as 1 unit up. You can do this everywhere here. Now, obviously, it started with the longer lengths, but if this is 1 unit down, that's 1 unit to the left. This is 2 units down. This is 2 units to the left. This is, sorry, we'll start up here. 3, 1, 2. I've made a mess here, but you understand what I'm saying. We're following that same pattern of rise equals run. And it goes one step further in that you can apply this to other areas of the drawing. And it does come into play that you may be asked to measure something that is not obviously related to this area. So maybe you have a section down here that is also in pink, but you've got no information. What you'll do then is you would take this rise of a run rule, you'd split up this typical rafter length, you'd split it up, divide it, and then multiply by how many units down, because 2 units down will mean 2 units to the left. So that's how you would find values elsewhere that might not have enough information for you, and you transfer it across. And there's something interesting, the similar concept going on with slope. Slope is the same story, it's just not 45 degrees. And all you're doing is saying, we have a dimension on plan, and what I usually do is I just say, well, it's 1 unit. I'm not interested in anything else, I just want, what is 1 unit? And if we have the slope, it's 28 degrees. All I want to know is, for every 1 unit this way, how many units would it be on slope? And that is just the cos 28 equals, that's the cos identity, which is adjacent over hypotenuse, right? 1 over x. And x ends up being 1 divided by cos 28. So once you get that, this is what we call the factor in MDA 1. And once you have your factor, you apply that. But what's behind this mathematics is the concept that we are interested in, basically rise and run. This is all it is. This, in fact, what's going on here is 2D, right? It's on flat. And what's going on here is the same concept, except it's now was 2D, but upright. It's the same thing. And I'd go far as to say, if this is 45 and this is also 45 degrees, it's the same concept being applied. It's exactly the same. For every 1 unit that way, this is also 1 unit up. Sorry, not that. That's Pythagoras there. Hold on, almost there. That is 1 unit up. Okay? That would apply to your slope as well. And over here, it would apply on your plan. 1 unit that way is the same as 1 unit that way. So, something interesting. You think about it from a conceptual point of view of what is actually going on in the background here. You grasp that and you'll be able to calculate pretty much anything, in my opinion. So we've covered that. The rafter, or the jack rafter divisions and lengths, I've covered in a previous video. I don't want to go over it again. Point number 7 is interesting because now we're going to apply the cos both forwards and backwards. And there's a trick here, and that is only rarely used to go backwards. But I think it could be used more often, and I think in assessment scenarios, this really could be taken advantage of to test our ability to think both forwards and backwards. So typically, we get a planned dimension. This one's probably better to take. And you apply your factor 1 over cos and your slope. Okay. That would convert it. But there's a scenario, only one that I've seen so far, where you need to find out what your length for your first batten is. So all we're saying is that you can apply cos to run up the slope, but there are instances where you need to reverse apply it. And that one instance that I've seen is where you need this first batten's length. And you don't need the other ones, but I'm sure it could be asked eventually. But this first batten, that length that is short is not actually its center to center dimension. So if we're saying a center to center is 345, that is center to center on slope. And we'll go over to this example. This is 345. But that does not necessarily mean that on slope is 345. In fact, it cannot be. This on slope is shorter than 345. And how much is it shorter by? Well, it's the reverse. You're going to have to divide 345 by 1 over cos 28. Okay, well, what we're saying is that even though it's 345 on slope, when it comes to this short bit here, this piece of timber, the first batten, runs from there to there. And if we want to calculate that length, you can't deduct by 345. That would be incorrect because that's just on slope. And since this length runs with the slope and not up the slope, our deduction must be on plan dimension because we're looking straight down. We're going to have to reverse engineer 345 to be 345 divided by 1 over cos 28. That is the one scenario I've seen where it goes backwards. I think there might be other instances. Now I'm not creative enough to figure that out. But I want to just take a look at the next one now. Point number 8, purpose made tiles. Now, let's actually go here. Purpose made tiles is specifically for between ridges and 2 hips. That's the description. But I want to just break down why it's important to understand what is going on in your drawing. You need to be able to visualize what exactly you're dealing with. Okay? And so when I see a drawing, I try and just visualize the faces of this roof and how it would work out. Because if you don't see the faces, it's hard to tell, for instance, what is this? Is this a hip rafter or a valley rafter? This one. Well, okay, obviously this end is a hipped end, so you got 2 hipped rafters there. But this basically decides how many purpose-made tiles you're going to use. So clearly you're going to say, well, Anthony, there's one. And I say, very good. That's halfway. And here's the other one. And this last little piece here, you might say, why not? Why not? And to be honest, I'll give you a guess. What we have here is not necessarily a sort of a ridge to hip scenario. What we have is a hip that's, it's going to come down slightly, this piece here. In fact, I want to call this a ridge, to be honest. it comes down slightly to this lower peak. And then we have a valley running this way. So valleys we ignore for obvious reasons. And then we have a ridge that continues. So all we have is a bunch of tiles sort of coming in this way. These are ridge tiles, by the way. I'm not sure if you can tell from my fantastic drawing, but it's changing angle slightly, and then it's sort of going this way. So our ridge tiles at this intersection do not need some sort of really elaborate purpose-made tile. I think they'll come up with a way of sort of waterproofing that and making it sealed. But in cases where you have a really intricate ridge coming in, sorry, that's not so good again, ridge, and then it actually splits into two sort of separate hipped ends, hipped ridges, you absolutely are going to need a purpose-made tile there. Okay? Just to waterproof that area, because they're all lapped. And suddenly you've got a change in direction, and not only a change in direction, but in two different directions. That is a cause for concern when it comes to waterproofing. And finally, I'm going to just come back to this valley here. If you cannot visualize that this is an entire face on its own, if you can't see that up front, you're not going to know that this is a valley over here. And you might say you need a purpose-made tile there. But all that is actually it's a recess in the roofing. Not a recess, but sort of, it's cut down. And that inside face is close cut and fitted is the description. But it is close cut and fitted all the way up to that point, and that's it. It's not requiring any lapping of tiles like the ridges. The ridges require lapped tiles and very intricately sort of waterproofed. It needs that membrane, that embossed damp-proof course, and it also needs a purpose-made tile. The valley is not the same, so you need to be really careful to visualize the drawing correctly. A lot of this stuff, in my opinion, comes down to how you visualize what you're dealing with. And if you don't visualize it properly, you could make a mistake. You're going to pay for it dearly. So that is that. The last point is the parapet walls, flashings and double flashing scenario, which is the first time I've seen. And I wouldn't say it's too advanced. You just need to sort of think logically. Flashing is wherever brickwork meets your roofing cover. So all we're saying is, in the past, we've typically sort of focused on an end where there's just a parapet wall and your roofing. But who's to say that I can't put a double pitch on that side? Hey, who's to say I don't want that going on? And then maybe I'm going to force you to measure, and I'm going to try and see if you can think flexibly about this. Are you sharp enough to notice that there's a flashing there and a flashing there? And so that is exactly what this drawing did. Right over here. Even though I can't really show it too well, let's just zoom in here. So this drawing will have, and this one's interesting, it's got two different versions of how to measure flashing. This flashing will be sort of a linear length without a factor, because this is coming back to what I said earlier. If it runs with a slope, there's no factor, and I can't draw it on this. If it runs with the slope, sort of along the slope, there's no factor, and this is for obvious reasons. It hasn't changed in altitude or length based on an angle or degree. However, this face does run up a slope, and so it does need a factor of 1 over, since it's 35 degrees, we'll say 1 over cos. 1 over cos 35. So this is an interesting point here, is that we've got two different types of sort of flashing calculations going on. Let me see if I can show this more clearly. This one is good. This is perfect. Okay. Take a look at this, guys. Oh, it's even worse than I thought. So this flashing is going to run this entire length. Okay. This flashing is going to run this length, but you're going to have to apply a factor. Okay. This one is a straight dimension. Okay. So hopefully this makes sense to you. Okay, because all I've been trying to really nail home here is that you have scenarios where even your ends could be running along a slope, no factor. And ends can be running up a slope. Okay, and the same thing is true for flashings. This flashing here is along. So no factor. And this one up and then back down a slope. So you're essentially going to take this length and simply apply a factor as if it was all running in the same direction. And again, this comes back to my theory that if you cannot visualize this stuff, you will get caught out. So it's very important that you start trying to see these drawings in sort of a three-dimensional way. You need to understand the dynamics of what's happening here. And if you can see things, you will not go wrong. Apply the rules. We know the rules. We just struggle to see where these rules are sort of coming into play. And there's a lot of interesting scenarios that could be asked. And try and play around with certain ideas, and you will find yourself actually realizing interesting questions that could be asked and preparing yourself in that way. So that is it. Parapet walls, flashings, and a double flashing scenario. That is it for today, guys. I thank you for listening. I hope it's been helpful. I'm open to suggestions, so please do message if you want a video on a specific topic. Otherwise, keep well. I will see you guys next time.